Hello everyone, welcome back to our channel. We are back again with a new video. In this video we are going to create a 3D conical surface using Python. So let us start this by importing the required libraries. So here NumPy, this library is used for numerical computations and working with arrays. In this code it is used to create arrays for the radial distance and the angle theta, as well as to handle the parametric equations for the cone surface. And matplotlib.pyplot is a plotting library that is used to create static, animated and interactive visualizations in Python. It's commonly used for generating 2D plots and charts. Here it is used to create a 3D plot for cone surface. And MPL toolkits. This is a toolkit for creating 3D plots in Matplotlib. It provides the functionality of 3D plotting and visualizations in 3D space. And now we'll define parameters for the cone. So here Rmax, this defines the maximum radius of the cone's base, and the cone will have a maximum radius of 5 units at the base. And H is, this represents the height of the cone, which is set to 10 unit, and it defines how tall the cone will be. And num points is, this is the number of points used to describe the radial distance r and angular coordinate theta, and more points give higher resolution in the plot. Here it is set to 100. And now we'll create the radial and angular coordinates. So here r is equals to np.linspace. This creates a 1D array of num point equally spaced values between 0 and rmax, which is 5, and these represent the radial distance from the center of the cone. And theta is equals to np.linspace. This generates num points equally spaced values between 0 and 2 pi, representing the angle around the center of the cone. And r theta is equals to np.meshGrid. This generates 2D arrays r and theta from 1D array. The r array represents the radial distance from every value of theta, and the theta array represents the angular values for every values of r, and these 2D arrays are the grid of coordinate used to define the surface of the cone. And now we'll define the parametric equations for the cone surface. So here x is equals to r into np.cos theta. This uses polar to Cartesian conversion, and the x coordinate is calculated by multiplying the radial distance r by cosine of the angle theta. and y is equals to r into np sin theta. Similarly, the y coordinate is calculated by multiplying the radial distance r by the sine of the angle theta, and z value is the z coordinate, which represents the height of each point on the cone's surface. At the apex of the cone, where r is equals to 0, the height z is equal to small h, the cone's height. As r increases towards r max, the height decreases linearly, so this gives the cone its tapered shape. And now we'll create the 3D plot. So here plt.figure, this creates a new figure for the plot with a specified side of 6 into 6 inches, and ax is equals to figure.add. This adds a 3D subplot to the figure, meaning the plot will be created in 3D space. So the 111 argument specifies a 1 into 1 grid and places the subplot in the first position. Now we'll plot the cone's surface. So here this function plots the surface of the cone using x, y and z coordinate calculated earlier, and the parameter used are CMap Inferno. This specifies the color map to use the surface, and the Inferno color map gives the surface a warm color gradient, yellow to red to dark, and edge color is K. This sets the color of the edges to the surface to black. K stands for black, and alpha is equals to 0.7. This sets the transparency of the surface to 70%, and the surface will be partially transparent, which allows for better visualization of underlying structures if needed. And now we'll customize the plot. So this sets the suitable title to the plot. And here ax.set x label, y label and z label. This labels the x-axis and y-axis and z-axis. And at last now we'll display the plot. So here we can see a 3D conical pattern. So thanks for watching this video.